Hi everyone, and welcome to the video lecture for Step 4 on making a measurement. In this lecture, we're going to go through the process of how you compare the histogram that we have for data and all of our Monte Carlo estimates in a statistical manner. So by eye, we can look at this and see that yes, the large peak in the data and the Monte Carlo is roughly the same, but what's the methodology we're going to use to create a statistical model and test a hypothesis rigorously? So looking in our web browser, we see there are, as usual, two commands we need to run. First, we're going to make a new directory. And then again, before I run fit.sh in bash, I'm going to open it up and read it. But this is pretty simple, so let's read fit.py now. So in fit.py, we are going to be performing all of the statistical modeling and fitting. The first thing we're going to be doing is loading in the data and backgrounds here. And then we're going to have to reperform this QCD estimate because we didn't save that out to a histogram. While we did actually calculate the QCD background estimate with our control region in the plotting step, we just displayed it and we never saved it. So this time we're actually going to recompute that QCD estimate and we're going to save it to this fitinputs.root file. That way, if we ever want to rerun, we have the input file. Now the next thing we need to do is set up the actual model. So we're going to be using roostats, which is a common root package in order to do this. And you can see that we are going to be creating a mu value for zeta tau tau. What that means is we're trying to compare the strength of the zeta tau tau signal in the data as compared to the standard model. Now, in doing that, there are a lot of different uncertainties we need to consider. First of all, the data has error bars because it's a counting measurement. That's pretty expected. But also there are potential systematic uncertainties in the luminosity and in the normalizations of all the different processes. So we calculated the cross-section for all the different processes shown in our web browser, zeta tau tau, W plus jets, our data-driven methods, but we don't actually know that we got those calculations exactly right. There's a little bit of an uncertainty on all of those. So what we're going to be doing is, for instance, setting some nuisance parameter like the luminosity, and then setting its error. So for in this case, we're going to have a 10% error on the luminosity. And we do the same thing for all of the systematics, as you can see here, for all the systematic uncertainties on cross sections. So as you can see here, we're adding all the processes and we're adding an overall systematic on their cross section. So we are going to create a workspace in order which to do this fitting. We're going to create a profile likelihood calculator and we're going to set its confidence interval to 0.68. So what that means is that we're going to be fitting a profile likelihood with all of the nuisance parameters, which are all of the uncertainties on the cross sections. And then we're going to set a confidence level of 1 sigma. So what we expect is some plot with 1 sigma bands on it at the end. Finally, we're just going to run the fitter and see what we get. So let's type this bash command. So really quickly, it just threw a lot of output at us. But what I'd like to draw your attention to is this table here where we have all of the parameters that we're floating. So this summarizes our nuisance parameters as well as our parameter of interest. So we see, for instance, luminosity. We set it to 1.0, but now we see that it was fit to 1.03. So what does that actually mean? So the luminosity is going to scale up all of the histograms. All of the solid colored histograms are going to get scaled up together with the luminosity. And while we thought we might have recorded 1 femtobarn of luminosity, it turns out that the best fit value is that we recorded 1.03 inverse femtobarns of integrated luminosity. And so that's totally within our uncertainty on the luminosity. We said it was 10%. And so that's fine. This is one of our nuisance parameters in our fit. It got pulled a little bit high, but it's totally within a 1 sigma band. And so that's how the profile likelihood fit works, is it's going to change some of the values a little bit, but in the end, it's going to be trying to get the best fit between data and Monte Carlo. Now the relative normalizations, not just the absolute normalization, can also change. So as you can see, our QCD cross-section was pulled a little bit high as well. So it was pulled 8% high. And that's fine. That just means that the QCD shape needed to be adjusted relative to other things like the Z to LL shape, which needed to be pulled a little bit low. So what we're doing is floating simultaneously all the normalizations, both relative to one another and absolute, on all of these solid colored histograms in order to get the best fit compared to the data. And we do that and we see that these are the values that come out, and they're all within the uncertainties that we set, and so nothing is really surprising us there. The last parameter that was floating was the significance the signal strength on zeta tau tau. This is what's going to be in our plot, but what we see here is that the value was 0.962, and that is pretty close to the expected value from the standard model of 1.0. But let's look at the plot to get a little more information. So I'm going to go to our fit area. And I'm going to open up fit.png. What you see here is totally in agreement with the plot in the web browser. So here you see that the signal strength best fit was 0.962, but that our 1 sigma error bands definitely encompass the standard model value of exactly 1. So this means that our experiment was in agreement with the standard model at the 68% confidence level. Okay, so that's everything that you should need to know in order to perform a measurement in this example. At this point, Jordan is going to be taking over from me with the lectures explaining continuous integration to all of you. So thanks for tuning in, and we will continue next time with Jordan.